Hello, my name is Mark, and it is follow-up video for my 8080 single-board computer project. In this part I want to discuss software part for different components of the system. Let's look at a simplified system diagram. Firstly, we need to develop some PC controlling software which would send memory image to memory controller that would be used by 8080. Then we need to write firmware for STM32 microcontroller. It would be quite simple firmware just because STM32 in my case only UART bridge. Then main part is FPGA gateware. It actually implements memory controlling logic and provide different signals to 8080. And finally, we are going to write some software for 8080 itself. So, let's get started. I would give you a quick introduction in memory organization for 8080 systems. It has same memory space for data and instructions, and this space could be up to 64 kilobytes of memory because of 16-bit wide address bus. It depends on hardware implementation how this memory space would be split between RAM, ROM and maybe some dedicated I/O space. There were such cases as Altair 8800 which had no ROM pre-installed and you had to buy it separately. In my system, whole memory would be RAM memory, except small portion of space that I reserved for memory mapped input-output registers. 8080 had separate instructions for input-output operations, but it is more convenient to have some memory mapped registers because I can access them through C code without any assembly in lines. Such simple memory organization means that our controlling PC software need just to send memory image to FPGA, and it could be done via trivial UART protocol. So why have I chosen STM32 as USB to UART bridge while there are plenty of other cheaper and simpler options on the market? It is mostly because I wanted to have backup plan. If something went wrong, I had a microcontroller with spare legs and I can implement some quick dirty hacks in software. Fortunately, it wasn't necessary, so in future revisions I can replace STM32 by FT232 or CH340 USB to UART controllers. And because of such simple role, firmware for STM32 is very basic. It uses standard HAL middleware from ST to implement USB SDC device, and from other end it has a ring buffer to retrieve data from FPGA via UART. Maybe one detail that worth to mention is that I'm flashing that ring buffer in main cycle of microcontroller firmware, and I don't want to send packets via USB with disabled interrupts just in case. So that's why I am copying content of ring buffer into temporal buffer and then enable interrupts and send it via USB. So that's simple, nothing to discuss more. As I mentioned, controlling PC software is also not going to be very complex. Basically, it needs just to send a memory image and trigger a reset signal for 8080 CPU. But I wanted to add a couple more features. First feature is to have two more commands to read and write separate bytes from memory. It would allow me to test the FPGA implementation of interface between FPGA core and embedded SRAM memory. And the second feature is some kind of input-output subsystem for 8080 itself. I wanted to have two kinds of interactions from 8080. First operation is request from 8080 to print current system host time. It would allow me to calculate average frequency because I can retrieve information about tick count. And the second operation is to print arbitrary data on terminal. I wanted to touch the topic because I also had to implement some kind of trick. UART protocol is quite straightforward. First byte is opcode and second byte is data byte. But it's not true for that last operation. For that operation I retrieve only single byte of data and print it. Why? To explain that I need to talk about one program. This program streams a lot of data via UART, and regular delay between bytes that it wants to send is 450 ticks, which translates to 150 microseconds. If we would calculate how much time it would take for a single byte transfer, it would be 10 bits, 8 bits of data, one start bit and one stop bit. For specified baud rate 150,200, it would take around 55 microseconds. For 2 bytes it would be 170 microseconds, which is bigger than delay between the transmit attempts. And at some point it would overflow my FIFO buffer and ring buffer. So that's why I had to implement that small hack. Now it's time to talk about 8080 input and output signals. First important signal is sync signal. 8080 uses that signal to inform periphery about start of machine cycle. Machine cycle defines one read or write operation for memory or device input-output subsystem. And shortly after rise of that signal, CPU outputs information about its internal state on data pins and about target address on address bus. We need to be careful while reading that data and address buses, because we want to read it in a particular moment when there is actual data on buses. And this moment is after falling edge of second clock signal. On that moment data is valid and we can orient and work with that information. Another important signal is dbin. For read operation, at some moment CPU raises that signal to inform periphery that it's ready to read data from data bus. And for write operation there is a similar signal, WR. So that's enough information to build a simple memory controller. Of course, in real systems it's much more complex, because I haven't covered interrupts or health states, or that fact that usually memory is slower than CPU, and that's why CPU should wait when data from memory would be available for read or write operations. But my memory is quite fast, so you can ignore that case. In my previous video I explained why I have chosen microchip iGlu2 FPGA, but one of the reasons was that it has embedded SRAM. So here it is, HPMS, High Performance Memory Subsystem. But I had to write extra ESRAM controller module, because HPMS is running on slightly lower frequency than my main system. It runs on 50 MHz, while my main clock signal is 180 plus MHz. So I had to implement a simple congestion module. Another utilitarian part of schema is UART. It's quite standard, so I'm not going to show it as well, but just want to mention that I had to add FIFO queue, because 8080 can produce output data faster than UART can handle it with specified baud rate. So I added a simple queue just to avoid loss of data. So first 8080 related module is clock generation module. It's simple and straightforward. From input clock signal I generate 2 clock signals for 8080. That's it. It's not 100% precise because of timings, but it's close enough. I have not reached maximum capability of 8080, but it's good enough for me. Next module is module to interface FPGA with PC. It just receives commands from UART interface and executes them. Commands are similar to each other, so I would show you implementation of a command to write a whole image to memory. All other commands are similar to that. Maybe except command to reset 8080 CPU. It's a bit different because we need to cross clock domains, so it need to synchronize signals. But other than that, it's straightforward. So now let's look into interesting part, interaction with 8080. At first, again, I need to synchronize signals from another clock domain, from 8080 clock domain to my main clock domain. I'm doing it just by using standard pattern, 2 flip-flops. And here is implementation, start of implementation of final state machine, which handles machine cycles of 8080. At first we wait for sync signal rise, and then we want to wait for falling edge of second clock signal to be able to read status information and to latch address bus as well. After that we can understand what operation 8080 wants us to perform, if it's a read operation or write operation, and jump to according our internal state of FSM. For read operation, it's again quite simple and nothing special. We just read data from SRAM and outputs it on top bus when DBin signal would be high. Maybe except the case when 8080 tries to access specific addresses. I emulate memory mapped input-output register, which contains information about current tick counts. So in that case, I just read tick counter and outputs it on data bus instead of reading data from embedded SRAM. Write operation splits into 2 branches. We could either write to the memory or output data byte via UART. Also, nothing special, all simple, as I want to keep my FPGA code. You can find all source code files in my GitHub repository. Finally, we can start to write actual 8080 code. I am doing it with the help of that 8080DK project. Originally it was developed for Z80, but it also supports 8080 and 8085 targets. But at first we need to create a couple of configuration files to declare our board. First file is a regular configuration file, which could be found for other targets. And it specifies machine type 8080 and points to different includes, libraries, CRTs, and so on. Another file is actual CRT initialization. there is two important constants. First constant is start of our code. In my case, my code placed at address 0000. And second constant is stack pointer. It also 0000. But important to notice that 8080 on push instruction first decrease stack pointer, and only after that writes data into memory. It means that when first push instruction would be executed, byte would be written at address FFFF, and then stack continues to decrease. So it means that our stack is placed on the end of memory. Another modification that potentially you need to perform if you are not using the latest version of Z8080DK is to apply that patch. Z8080DK has a set of optimizations that done on assembly level, and for some reason they forgot to put directives for that optimization that could be performed only for Z80. But 8080 and 8085 would be just broken because of incorrect instruction would be inserted. So after that we can build our source code. Just call ZCC with a list of files to be compiled, output at binary name, and that's it. Maybe you can notice hal.asm. It's just a small assembly file with machine-specific commands to work with terminal. So it's print one character and read one character. I implemented only print, and this character would be sent via UART to my host PC. Z8080DK also provides math library, so we can use mathematical operations for different types. Not only 8-bit types, 8080 is 80-bit processor, but also 16-bit types, 32-bit types, 64-bit types. So it's all done under the hood. But worth to mention that type conversion is a bit broken on ZCC. So you sometimes need to specify concrete types of all arguments to let ZCC generate proper code. Here is an example of how I retrieve information about tick counter. As I mentioned, it's done by reading a pointer from a specific location in memory, our memory mapped register. And I don't use any assembly lines. Before running code on real hardware, I want to test it on emulated environment. Usually I wrote emulators by my own to better understand target architecture. But in that case 8080 is simple enough, so I have used that open source library. Of course I had to make some modifications. At least we need to implement that memory mapped register that provides tick counter. And also because some of my programs ran for a couple of days, clock counter has been overflown, so I had to change it to some bigger type, big integer. After that, usage of that library was pleasant, and I easily attached it to my code. Maybe another modification that I had to make is to implement pseudo device that would coach output from 8080 and display it on console, inside my terminal. After that, I extended my emulator in a couple more modes. First mode is a profiling mode, because I wanted to write some kind of optimal code and wanted to determine bottlenecks. Fortunately, that 8080DK provides a symbol map, so I can determine what function it is based on its address. So profiling was easy. Debug mode is also quite straightforward. I implemented simple command terminal which supports commands to set breakpoint, to read memory content, to jump to next instruction. And after that I was able to debug and fix all my programs in emulator, and it was ready to be uploaded on a real device. First program that I ran on real hardware, beside the Hello World of course, was Dhrystone benchmark. It is quite old benchmark, but there is still data for modern processors, so it was quite interesting to compare my results with fresh CPUs. It doesn't require a lot of modifications to support my board, just need to modify function to read tick counter from memory mapped register, and that's it. After that I got results. They were not so promising, but quite disappointing. Only 0.06 DMIPS. In comparison, not so modern but quite decent Core i7 has 23,000 of DMIPS. Also, Raspberry Pi has around 3,500 of DMIPS. So in that comparison, 8080 looks very weak. But if we look into some lowest score which I have found for Dhrystone, I can see that 8080 can beat Commodore 64 and Apple IIe, which is surprising. So, not that bad. After Dhrystone, I started to look into more modern benchmarks and found out that CoreMark is actually quite portable and could be run even on such a low performance platform. I ran it and unsurprisingly got very low results. It's actually on the end of the list. Still, it was quite interesting experience. In the next video I want to explore possibilities of 8080 more and going to write program that computes digits of pi by using Chudnovsky algorithm. To do it efficiently I had to write my own big number arithmetic for 8080, and more interestingly I had to investigate fast methods of computing square root for such big numbers. It would be something like Karatsuba method for multiplications, same divide and conquer principle. Hope that this video was not so boring, and see you next time. Bye.